The current code effectively sets up a pipeline for training and evaluating a BreastMNIST classifier with functionality for data augmentation, handling class imbalance, saving checkpoints, and generating Grad-CAM visualizations. However, there are areas to review and modify to align with the goal of integrating results into a display like rhythm scans. Here's an overview and instructions for necessary updates. 1. Data loading and preprocessing. The current code loads data from an .npz file, normalizes it, and reshapes it to include a channel dimension. Ensure the reshaping is consistent for all inputs and verify that normalization is applied correctly to prevent errors during training or inference. 2. Class imbalance handling. The code calculates class weights using compute class weight, which is good for balancing the loss function. Confirm these weights are passed correctly during training and review whether additional augmentation of the minority class might help further. 3. Training parameters and callbacks. Training parameters are dynamically input by the user. You might streamline this by setting defaults or optimizing batch size and learning rate based on experiments. Early stopping and checkpoint saving are well implemented, but should ensure the best model is saved for evaluation. 4. Grad visualization. The code generates a Grad-CAM heat map for a single test image. Expand this functionality to allow generating Grad-CAM visualizations for misclassified images or specific samples of interest. Save these visualizations in a structured format for later display on the web interface. 5. Performance metrics and visualization. The script prints evaluation metrics and saves models, but does not save accuracy loss curves or confusion matrices in a reusable format. Update the script to generate and save plots for these metrics in designated directories, ensuring they are easy to access for web display. 6. Misclassified images. While the confusion matrix is generated, misclassified images are not explicitly identified or saved. Modify the script to save a subset of these images, including their true and predicted labels, for detailed analysis. 7. Model conversion for deployment. TensorFlow.js conversion is included as an optional step, which is appropriate for browser-based deployment. Verify the converted model works correctly and ensure the directory structure for storing these files is clearly organized. 8. Output structure. Organize all outputs, metrics, visualizations, Grad-CAM images, misclassified examples, and logs into a structured directory hierarchy, making it straightforward to integrate them into the HTML interface. These changes will align the script's output with the goals of displaying detailed performance metrics and visualizations while preparing the model for efficient deployment. Let me know if you need further clarification on any step. I've updated the code to ensure reshaping is consistent for all inputs and added a verification step for normalization, making sure it's correctly applied. I've updated the code to confirm that class weights are properly used during training and added additional augmentation to address the imbalance in the minority class.
Yes, what we did really quickly is, by the way, go check out this vision impairment simulator. But what we are doing, we have this new dataset that we're looking at. It's called BreastMNIST. Has benign and malignant CT scan images.
I've streamlined the training parameter input by setting default values for epochs, batch size, and learning rate. Additionally, I've ensured that only the best model is saved during training by modifying the checkpoint callback settings.
Anyway, obviously the robot can explain it much better than I can, than I could ever explain anything. I think it's game over for teachers.
I've expanded the Grad-CAM functionality to generate heat maps for all misclassified images. These heat maps, along with their associated metadata, are saved in a structured format for later use on the web interface.
Okay, we'll need to update, obviously, the front end as well. Just need to do another round of training. We did 2 training runs already. We didn't get we got like 0.7 or so, as opposed to 0.9 for area under the curve. So we're trying to improve the model performance. We have apparently a much simpler model than ResNet 18. Well, definitely simpler than ResNet 50, but that's okay because we don't wanna increase the model complexity unnecessarily. Yeah, so we're making some changes. We have another developer, another tab of ChatGPT, which is essentially another developer updating the code for us, and I'll share the updated version with you below.
I've updated the script to generate and save accuracy loss curves, confusion matrices, and classification reports in designated directories. This makes it easier to access these metrics for web display or further analysis.
Yeah, this impairment simulator, I can actually hear my CPU, GPU going. It's a bit too heavy, especially when I'm making changes on the page. I think it must be the GPU then. Yeah, I don't know if there's interest. We might look into redoing it from scratch. That one from memory is a Flask application, but we are gearing towards doing vanilla JavaScript because it's then can be streamlined and much quicker for the end user as well. You want to close it. I save a lot of electricity by not using it, but yeah, let me know what you think.
I've modified the script to save a subset of misclassified images along with their true and predicted labels for further analysis. These images are saved in a dedicated directory, making them easy to access for review. I've updated the code to ensure the TensorFlow.js converted model is saved in a clearly organized directory, TensorFlow.js course model. This helps keep the directory structure tidy and makes it easier to locate the converted files.
Yeah, so I'm not sure if it's a problem specifically for... If it's a problem for this specific for or with canvas thing, it keeps giving me errors that the code is too long. That's a bit unfortunate. So we did everything up to 6. We did everything up to change recommended necessary update number 6. So we would like to stage it and do the rest separately. But can you check the script so far? Yeah, give a quick overview. Don't generate any code yet, just tell me what's going on. So we have another developer essentially implementing changes that you suggested. He went over 1 to 6. So we still haven't done 7 and 8, but can we check the code up to this stage? It's going places now.
The updated code implements significant improvements based on earlier suggestions, addressing points 1 through 6 and partially covering point 7. Here's an overview of the changes and what remains to be done. Overview of the current code. 1. Directory setup. Separate directories for checkpoints, training plots, misclassified images, and Grad-CAM outputs are now created, ensuring better organization of results. 2. Dataset handling. The dataset is normalized, reshaped, and augmented appropriately. Class imbalance is handled using a mix of class weights and additional augmented samples for the minority class. 3. Training parameters. Defaults for training parameters like epochs, batch size, and learning rate are provided, and user inputs are streamlined. This makes the process flexible while maintaining clarity. 4. Model definition and training. The custom CNN model is well-defined, and callbacks such as early stopping and checkpoint saving ensure efficient training and model preservation. 5. Performance visualization. Accuracy and loss plots are generated and saved, providing a clear visual representation of model performance over epochs. 6. Evaluation and outputs. The test set evaluation generates accuracy, AUC, a confusion matrix, and a classification report. These outputs are saved as images and JSON files for further analysis. 7. Grad-CAM visualization. Grad-CAM heat maps for misclassified images are generated, saved, and accompanied by metadata in JSON files, which is excellent for interpretability. Remaining changes. 1. Model conversion for deployment, point 7. While the TensorFlow.js conversion code is included, it depends on user confirmation. Ensure this process works seamlessly and validate that the converted model performs as expected in a web environment. 2. Streamlined results for front-end integration. Point 8. Results such as Grad-CAM heatmaps, misclassified images, accuracy loss plots, and confusion matrices should be packaged or referenced in a structure compatible with the front-end interface. Simplify access for visualization on the HTML page. Suggestions. Moving forward. The updated code is well aligned with the training and analysis goals. Focus now on ensuring that results integrate smoothly into the web interface. Validate the TensorFlow.js model on example inputs to ensure it matches the Python-trained model's performance. If performance issues persist with the GPU usage on the front end, consider simplifying front-end visualizations or caching results to reduce runtime load.
Okay, we'll try it again. I'm not sure why is it saying the code is too long. Well, I mean, yeah, it's currently just over 300 lines. That should be okay, shouldn't it? So let's actually try doing a change number 7, see how it goes. It seems like the chat doesn't know what's happening in the canvas. I actually got an error message when generating the code. I got an error message that it's too long and the code in the canvas got truncated. Can you just comment on that? We might need to stage the code, split it in two. Yeah, edit comments. Yeah, I think it doesn't know what it's talking about. No, there's something wrong. Yeah, we might need to split the code. Yeah, I'll close this canvas thingy. Currently train 200 lines. This will be like 300. Let's do a training run. See how we go. Yeah, so it's asking us to enter a number of epochs, or we can just hit enter for the default of 15 to be used. Same batch size, default is 32. A learning rate 0.001. That's okay. Proceed with training of 15 epochs, batch size 32. Learning rate, yes. You have to type in yes. And we are training. Yeah, I can't really see the results really well from here, but yeah, I'll just let it train. Okay, it finished at accuracy of 0.7 and area under the curve of 0.8. But the loss is high. Do we want to convert the model to TensorFlow.js? Yes. We get an error. Get an error. Yeah, we have no web model. I think it meant to be stored in the web model. We have misclassified images. No, which is weird. Heat maps, no heat maps. Model checkpoints. Okay, we have training plots. Training and validation accuracy. Yeah, those are not great, are they? They are not great. So do I upload the image or the actual text results? Yeah, if you can comment without any code, that will be greatly appreciated.
These plots show the training and validation accuracy and loss over 15 epochs. The training accuracy steadily improves, but validation accuracy fluctuates significantly, indicating potential overfitting or instability during training. Similarly, the training loss decreases consistently, while validation loss spikes and falls irregularly, suggesting that the model is struggling to generalize to the validation data. To address this, consider 1. Regularization. Increase dropout or add L2 regularization to reduce overfitting. 2. Data augmentation. Expand augmentation techniques to provide more varied data for better generalization. 3. Learning rate adjustment. Reduce the learning rate to stabilize training and validation performance. 4. Class imbalance. Double check if the minority class is adequately balanced with oversampling or augmentation. The training script has run into several issues during execution, which need to be addressed sequentially. 1. Training results. The training process completed with a test accuracy of 76% and a test AUC of 0.81, which is moderate but below the desired performance. The training loss consistently decreased, but the validation metrics, accuracy and loss, fluctuated, indicating potential overfitting or instability in the training process. 2. TensorFlow.js conversion error. The TensorFlow.js model conversion failed due to a duplicate weight name, kernel, in the model, which suggests an issue with the layer naming or saving process. This needs debugging by ensuring all layers have unique names or exporting the model in a consistent format, e.g. .keras format instead of DH5. 3. Grad-CAM error. The Grad-CAM visualization failed because the model has not been explicitly called on any input data before attempting to access its layer's outputs. This can be fixed by running a dummy prediction, model.predict, on a sample input before generating Grad-CAM heatmaps. 4. GPU registration errors. Warnings related to GPU libraries, QFT, QDNN, QBLAS, indicate potential conflicts or redundant initializations, but they don't appear to affect the training directly. However, they should be addressed by reviewing your GPU environment setup to avoid unnecessary resource usage. Steps to fix the issues. 1. Model conversion. Remove the deprecated save format argument from model.save calls. Explicitly save the model in .keras format for conversion. Debug the duplicate weight issue by inspecting the layer names and ensuring they are unique. Consider reinitializing the model or using a simpler structure if necessary. Grad-CAM fix. Add a dummy forward pass using model.predict xtest1 or model xtest1 before calling make Grad-CAM heatmap. 3. The code can be split into modules for better organization and flexibility. A data loader module will handle loading, pre-processing, and class balancing. A model definition module will define and compile the CNN and handle saving or converting the model. A train model module will handle training, callbacks, and saving logs or plots. An evaluation module will manage evaluation, confusion matrices, and Grad-CAM visualizations. A Frontend utils module will package results for the web frontend and handle TensorFlow.js validation. Finally, a main script will coordinate all modules for end-to-end execution, ensuring modularity and easier debugging.